Welcome back. Okay, so today I'm going to tell you about how we can solve partial differential equations using the Laplace transform. I've been looking forward to this lecture for a while. So I gave a lecture on Laplace transforms and how they relate to ordinary differential equations, well over a year ago. And I have had a series on vector calculus and partial differential equations for a while now. And now I'm excited that these two can meet in the middle. So we're going to solve PDEs using Laplace transforms. I think this is going to be two videos. In the first one, I'm going to show you how to solve the heat equation using Laplace transforms. And in the second video, I'm going to show you how to solve the wave equation using Laplace transforms. And this is a really, really powerful technique to solve PDEs. So remember, Laplace transforms for ODEs, they turn ordinary differential equations into algebraic equations. They're going to turn partial differential equations into ordinary differential equations. So Laplace transforms almost always make your problem simpler to solve. And in the case of PDEs, it's going to make it simpler to solve by turning them into ordinary differential equations. Okay, good. And we have, for a long time now, known how to solve partial differential equations using the Fourier transform. So I have a bunch of lectures on how to do this numerically using the FFT to numerically solve PDEs, either on periodic domains or on infinite domains. But also analytically. We know how to solve analytically PDEs using the Fourier transform. And Fourier transforms are good for PDEs on an infinite domain, kind of where x goes on forever, negative infinity to positive infinity, where we have decaying boundary conditions. So if I had, a thin metal rod that went on forever, and I have some temperature distribution in the middle, I can solve for the kind of heat equation as that evolves in time using the Fourier transform if I have infinite decaying boundary conditions. But remember, the Laplace transform is basically like a Fourier transform for nasty one-sided functions. And so just like I can solve PDEs on an infinite domain with good boundary conditions with the Fourier transform, I can solve PDEs on a semi-infinite domain, on kind of a one-sided domain with other boundary conditions using the Laplace transform. Good. So Laplace transforms are good for PDEs on a semi-infinite domain. Maybe I'll write a couple of little notes to myself. So these are good. Laplace transforms are good for PDEs on a semi-infinite domain. Semi-infinite domain where I have boundary conditions and an initial condition. So where I have boundary conditions and initial conditions. With BCs, let's say with a boundary condition and initial conditions. And so here I'm going to illustrate this on the heat equation, UT equals UXX. We derived this a few lectures ago, conservation of thermal energy in a metal rod. But here, instead of our metal rod going on from negative infinity to plus infinity, here it's just going to start at x equals 0. It is going to be semi-infinite, so we're going to assume that that wire goes on forever that way, or at least it's so long that it doesn't, for my purposes, it's approximately infinite. And we have an initial condition, some initial temperature distribution. Maybe I'll write it down. Our initial condition is going to be U. U is the temperature at every location x at every time t. And so our initial condition is U at every point x at time 0. And I'm actually going to solve this for a specific initial condition and for a specific boundary condition. You can figure out how to solve this for generic initial conditions and boundary conditions later. I'm going to assume that my initial condition is sine of 4x. So I kind of drew this wavy sine wave. That's my initial condition. Let's write it here. This is my initial condition. And I'm just going to tell you one of the punchlines is that when you Laplace transform this partial differential equation, this initial condition is going to act just like the forcing term did when we Laplace transformed our forced ordinary differential equations. So remember from like control theory or systems theory, when you have your ordinary differential equation plus forcing and you Laplace transform it, the way that that forcing enters is exactly how these initial conditions enter this problem. They're going to enter as forcing. So this is kind of like a forcing term, and you'll see that in a little bit. And I'm going to try to be color-coded here if I can. My notes got printed in grayscale, so it's going to be a little bit of a fun exercise for me to see if I can remember what colors go where. So we have an initial condition, and we also have a boundary condition. And I'm just going to assume that my boundary condition is on the left. And what I'm going to do is I'm going to impose a temperature on this left boundary condition. Maybe I have like a little heater and some controller, some PID controller to make that, you know, a constant or a temperature that I prescribe at this left boundary condition. And so that's going to be u at position x equals 0 for all of time t. I'm just going to specify that the boundary condition I'm choosing with my little controller is that the temperature at this point is e to the minus t at x equals 0. Maybe I'll just be very explicit. This was at time t equals 0. And so that boundary condition, if I look at this, you know, if I plot kind of u of t versus t, we just have some exponential decaying temperature at this left boundary condition. And again, you know, maybe I have some little radioactive element that's like exponentially decaying. Maybe I have a little heater and a PID controller, and I'm just specifying this temperature profile. It doesn't really matter, but this is the problem we're going to set up. So it's a heat equation on a semi-infinite domain with an initial condition and a boundary condition, and we're going to solve it using Laplace transforms. Now, I can't neglect this opportunity to remind you that although these techniques are very powerful, they are also a little bit anachronistic and antiquated. So we still definitely want to understand how partial differential equations work kind of intuitively. And one of the best ways we can intuitively understand how these work is through things like the Fourier transform or the Laplace transform. But these techniques were developed hundreds of years ago to solve problems with pencil and paper. And so you'll see in textbooks and in lectures, almost all of the examples that you actually have solutions for are on these kind of idealized domains, right? We solved the heat equation, Laplace's equation earlier on a rectangular domain because that's the only domain, not the only, but it's one of the only domains you can easily solve it for on one blackboard in 30 minutes. There are, you know, transformations, so I can solve it on a circular disk or on a semi-infinite domain. But solving for the heat distribution on an F22, that's a hard problem, and it's very hard to do it analytically with pencil and paper. So we need to use computers for those solutions. But it's still important to understand these canonical configurations and these classical solutions so that we gain intuition when we use computational solutions or even, you know, more recently machine learning solutions. So just a reminder, you know, we do these things on idealized domains because that's what we can do on pencil and paper or on a light board. And because that's what the tools, you know, admit solutions for. But those solutions still give us lots of intuition when we apply these to more complicated systems. Good. OK, so the goal now is we're going to solve for u of x comma t on the domain on x is, you know, greater than or equal to 0 and less than infinity, and time is, you know, greater than or equal to 0. So that's, and also less than infinity. Now, here's where it gets kind of interesting. So we're going to Laplace transform this PDE, and we're going to use these initial conditions and boundary conditions to try to solve this system. But I have a choice of what variable to Laplace transform with respect to. I could Laplace transform in time, I could Laplace transform in space, and until you get some intuition for this, it's not that obvious which one's right. So I actually often ask my students, you know, at this point in the lecture, like, which one should we Laplace transform? Should we Laplace transform time or space? And it really depends. What you're going to start building intuition for is it really depends on your initial conditions or your boundary conditions. Kind of what initial information you have will determine if you want to Laplace transform in space or in time. So in this one, I'm just going to kind of tell you the answer. We're going to Laplace transform in time, specifically because of the nature of our, we have the initial condition to do a Laplace transform in time, because we have one derivative in time. And so when I Laplace transform, I'm going to need one kind of initial condition in time, and I have one initial condition in time. If I Laplace transformed in space, I would need two boundary conditions somehow, because I have these two derivatives, and I've only got one boundary condition. So that's kind of one hand-wavy answer for why I want to Laplace transform in time and not space. And we'll revisit this at the end of the lecture. So good, so we're going to Laplace transform with respect to time. So kind of Laplace, this is my notation for Laplace transform with respect to, so this is a lot of math notation, Laplace transform with respect to time, the time variable with respect to time, with respect to time t. We're going to Laplace transform with respect to time t, and we're going to use our initial condition when we do that. This is because we have a single derivative in time and one initial condition. Okay, so for example, when I do in the next lecture, I'm going to do this for the wave equation, utt equals uxx. Now I've got two derivatives in time and two in space. So if I have two initial conditions, I'll Laplace transform in time. But if I had two boundary conditions, I would Laplace transform in space. So you really have to think about which what you have enough initial data to Laplace transform with respect to. Okay, so this is the easy part. We're just going to do the Laplace transform. We're going to Laplace transform with respect to time. And so remember that if I Laplace transform with respect to a variable, I get something like S is my Laplace transform variable, my frequency domain variable. This is kind of the analog of the Fourier frequency for Laplace. S times u bar is my Laplace transform of u. And now this is now no longer a function of space and time, it's a function of space and my Laplace variable s. So this is a function of x and s, because I'm Laplace transforming with respect to time, minus u of x comma 0. So this is going to, again, have the same, this is going to act like a forcing term. This equals the Laplace transform of uxx. And again, these are derivatives with respect to x, not with respect to time. So it's basically u bar xx. It's the second partial of u bar, my Laplace transform state u, with respect to x. So this is just u bar xx. You'll have to convince yourself that when you have a function u that's a function of space and time, if I only Laplace transform with respect to time, then I get u bar of x comma s. And if I, for example, take the second spatial derivative of that, it's just u bar xx. That's totally fine. So all I've done by Laplace transforming is I've removed this time derivative and turned it into s times u bar. But in doing so, now this is an ordinary differential equation in x. I have u bar and its derivatives in x, but I have no other partial derivatives. So this is an ordinary differential equation in x that I can solve. Good. So this is, I'm just going to write that out. This is an ODE, squeaky ODE in x, and it's second order. And if I really wanted to, I would say, I'd move stuff over on the same side, and I'd say this is, maybe I'll just do that. This is going to make my life easier. So this is, uxx bar minus s u bar equals minus u of x comma 0. Okay, and remember this is going to be my forcing term. This is not Laplace transform. This is actually this initial function of x. This is a function of x. These are Laplace transformed quantities, u bars. And so the way you solve this ordinary differential equation with forcing is first you act like the forcing is 0, and you find the homogeneous solution with forcing 0, and then you add on the particular solution that satisfies this particular forcing on the right-hand side. So essentially we have the homogeneous and the particular solution. I'm just going to write these down because it's pretty easy. So essentially what we have is, I'm just going to stick with yellow here. So essentially what we have is u bar of x comma s, this is my Laplace transform temperature, is equal to, if this was 0 forcing here, essentially this would be a second order ordinary differential equation u double prime minus s times u. And so the eigenvalues are plus or minus square root of s. Plus or minus square root of s. So I have some constant a, e to the minus root s times x, plus another constant b times e to the plus root s x, plus whatever my particular solution is of x comma s. Okay, and if I was being really clever, I would have color-coded this pink because this is my, due to my forcing term, this is my particular solution. Particular solution. And if this is going over your head, you might just want to, dust off your Boyce and de Prima or your ordinary differential equations. I'm sure I have some lectures on this, or I'll be making some, where if you solve an ODE with forcing, you act like the forcing is 0 to get the homogeneous part of the solution, and then you add on to that this particular solution that satisfies that forcing term. Okay, this is kind of how we've always done it. And I'm going to make a point. These constants out front, those constants need to be determined, just like, again, based on your initial conditions or your boundary conditions, just like you would normally do in ordinary differential equations. You would determine these coefficients by, like, the first and second derivatives, u at 0 and ux at 0. But now, because this is a Laplace transformed function, these are actually going to be Laplace domain functions. These coefficients are like Laplace functions. I'm not going to explain that again. we're going to assume that these coefficients are functions of the Laplace variable s, and then we're going to see that those need to be functions of the Laplace variable to satisfy the initial conditions and boundary conditions. Okay, so we Laplace transformed in time. We haven't used our initial condition yet, but we can see that we're going to find our particular solution. And we have determined that this is the basic form of the homogeneous solution. Now we know that for this to be a bounded solution as x goes to positive infinity, this term has to be 0, this b has to be 0, because e to the plus exponential in x grows without bound as x goes to infinity. So this term has to be equal to 0. This b has to equal 0 for what we call a bounded solution, which is kind of another boundary condition, if you think about it, is that we want our solution to be bounded as x goes to infinity. So this is the only term we have for the homogeneous solution, plus this particular solution. Okay, good. So I am going to determine this particular solution using my initial condition. And then I'm going to determine what a bar of s is using my boundary condition, using this boundary condition. So that's the last. We're going to essentially solve for this using, we'll use our boundary condition. So here we're going to use our initial condition. and here we're going to use our boundary condition. And so that's kind of the next 2 steps in this procedure. So we have taken this problem, Laplace transformed in time. The basic solution has to have this form. We killed this term so that we have a bounded solution. And then the particular solution, we're going to choose to satisfy this initial data forcing here. And this a bar of s we're going to determine using our boundary condition. Okay, this is going to be a little messy. There's no way around it. So I think what I'm going to do is I'm just going to barrel through. And we're essentially going to determine this particular solution using our initial condition. And I'm going to try to stick with pink as much as I can here. So we're going to find psi bar of x comma s. We are basically going to assume we know that it is going to have the form of whatever x of x comma u of x comma 0 is, which is sine of 4x. And so the way that you usually find a particular solution is that you assume that your solution is going to have the same form of sines and cosines of 4x. So we're going to assume that psi bar of x comma s is equal to sum of cosine of 4x plus a sine of 4x. And again, these are going to have undetermined coefficients. There's going to be some Laplace c of s and some Laplace d of s. And we're basically going to find the c of s and d of s that if I plug this in to this differential equation, it satisfies that u of x comma 0 equals sine of 4x, okay? Because this is my initial condition that we're plugging in here. That's how undetermined coefficients works. You just kind of guess a form of the solution that, if you took a bunch of derivatives, you might get something that's kind of like that forcing term. And then you determine the coefficients so that when you plug it into that differential equation, you exactly get that forcing term and you get this thing equal. Okay, this is a bit of a mess. So what am I going to do? I'm literally going to take psi and I am going to plug it in to this equation. Is that right? Yep, that's what I'm going to do. So I'm going to take s times psi minus sine of 4x equals the second derivative of psi with respect to x. It's a mess. Okay, so s times psi is s c of s cosine. And I'm not going to keep writing cosine 4x, sine of 4x. I'm just going to write cosine plus s times d of s sine. Okay, that is s psi minus u of x comma 0 minus sine 4x equals psi xx. I'm literally plugging psi in. Every time I see a u bar, I'm plugging in this psi, and I'm taking its second derivative here with respect to x. And I'm going to do it in my head, I hope. So the second derivative of cosine 4x with respect to x, the first derivative is minus 4 sine 4x. The second derivative is minus 16 cos 4x. So I'm definitely going to have a 16 times minus c bar s cos. And the second derivative of sine, again, is minus 16 sine. So minus, maybe I'll pop this negative sign out front. So I get a minus 16 cs cosine plus ds sine. And I'm just going to check my notes because it would be a disaster if I botched this at this stage. I'd never find what went wrong. So this is correct. sc cos plus sd sine minus sine minus 16c cos minus 16d sine. Good. Okay, and this is psi bar xx, and this is my initial condition forcing. Okay, so it seems like it's kind of hairy, but it's literally just like you could do this if someone woke you up at 2 in the morning, you could do this algebra. It's a little irritating, but it's not difficult, okay? So we are trying to determine this particular solution, so we plug it into the partial differential equation, assuming that it has a form kind of like the thing, you know, that are forcing terms, some sines and cosines of 4x. And now I'm going to collect all of my like terms and try to get a function, an expression for c of s and d of s. And so I think what this is going to be is something like, how's this going to work? We basically are going to collect all of our cosines on one side in one term and all of our sines in one term. So all of our cosines, we have s, c bar s. If I move this over, I get plus 16. C bar s cosine 4x plus, now I have s d of s, s d of s minus 1, well let's say minus, you know, plus 16 d of s, because I'm bringing this term over, this has a sign on it, minus 1. All of that times sine 4x, and we know that all of that had to equal 0. So all I'm doing is I'm just moving all of my cosine terms over and grouping them, and all of my sine terms over and grouping them, and that will have to equal 0. So this is all my cosine terms, this is all my sine terms. And now for this to be true for all of x, this has to equal 0, and this has to equal 0. And so that means that c of s clearly has to be 0. So c of s has to be 0. And d of s is basically s plus 16 d bar of s equals 1, implies that d bar of s equals 1 over s plus 16. Good. So we essentially have determined now that our particular solution psi is equal to 0 cosines plus 1 over s plus 16 sine 4x. And this is where it gets a little funny. You'll have to convince yourself. You have to go through the various steps, each point, and convince yourself, yes, in fact, this undetermined coefficient out here is not a constant. It's not a number. It is a, well, it is a constant with respect to space, because this is Laplace in time. But it is not just a number. It's a whole Laplace transform function, a transfer function d bar of s. So I'm just going to write this down so that I don't forget it. So psi of x comma s equals 1 over s plus 16 quantity times sine 4x. This is my particular solution to this ODE. So this is one piece of the solution, and now I need to find the homogeneous solution. So we used our initial condition to find the particular solution. I just wrote it down here. We're going to save that for later. And now we need the boundary conditions to solve for this homogeneous solution. Okay, good. I hope you're all with me so far. Maybe I'll do a quick little recap, and then we're going to keep going. This is a long lecture. I'm going to make sure. Okay, I got battery for now, so I better hurry. We are solving this PDE in space and time using the Laplace transform. Remember, when we solved the heat equation in steady state, we didn't think about how things evolved in time. We just solved in the limit of t goes to infinity. So to solve how things actually evolve in space and time is a little more tricky. You either need the Fourier transform on an infinite domain or the Laplace transform if you have a semi-infinite domain. Since we have semi-infinite, we're Laplace transforming with time. And when we Laplace transform with time, the initial condition acts like forcing, and the boundary condition is going to be how we solve for this a bar of s in the homogeneous part of the solution. Homogeneous solution, particular solution. So now we're going to determine this a bar of s using our boundary condition. And once we've done that, we will now have this, this will be determined and this will be determined, and all we'll have to do is inverse Laplace transform with respect to time, and that'll be our solution. So that's all we have to do now, and I hope this isn't too difficult, and maybe I'll do this one in blue. I want to give myself some space here to work so that I don't cut my head off. So I think now we determine a bar of S essentially by setting x equal to 0 and using our boundary condition. Okay, and using our boundary condition. Okay, good. So we're going to set x equal to 0 here. Sine of x equal to 0 is 0. E to the minus root s 0 is just 1. So essentially, if I set x equal to 0, u bar of 0 comma s is just equal to a bar of s. That's really simple. That's really, really simple. And we know that u bar of 0 comma s is equal to the Laplace transform of our boundary condition u at 0 comma t, u at 0 comma t, which is the Laplace transform of e to the minus t. And the Laplace transform of e to the minus t is just 1 over s plus t. 1 over s plus 1. This equals 1 over s plus 1. Sorry, I shouldn't have said s plus t. So a bar of s equals 1 over s plus 1, because that's the Laplace transform of my boundary condition. So now I have my homogeneous solution and my particular solution, and I can combine them. Okay, so this is the last step. I'm done after this, so don't panic. We're basically done. So now what we have is the solution in the frequency domain. So the solution in the frequency domain, and I'm just going to write this out, is u bar x comma s equals the homogeneous solution, which is 1 over s plus 1. And now you see why this undetermined coefficient is a function of the Laplace variable s. It's not just a constant, it's a transfer function, which is a constant with respect to space, again, because this is Laplace transform in time. So, this whole thing is a constant as far as space is concerned. But this is a transfer function. It's 1 over s plus 1, e to the minus root s x plus the particular solution plus 1 over s plus 16. I hope that's not s, yeah, that's s over 16 sine of 4x. So to some extent, we're done. This is the solution of my PDE. This is the Laplace transform of my solution. So for example, if I took this initial condition and this boundary condition and I simulated it forward in time, I could essentially Laplace transform that solution and get this. This is the Laplace transform of the solution at instead of this being a function of time, this is a function of the Laplace variable. So now the last thing is, if I want to get back a solution in the time domain, I have to inverse Laplace transform this. So in the time domain, we essentially say u of x comma t. This is too faint. I'm just going to go back to yellow. U of x comma t equals the inverse Laplace transform of this whole thing. And remember, if I inverse Laplace transform, the inverse Laplace transform of the product of two functions is the convolution of the inverse Laplace transform of each of those functions. So this is Laplace transform inverse of 1 over s plus 1, convolution integral with the inverse Laplace transform of e to the minus root sx, plus the inverse Laplace transform of this thing, which is 1 over s plus 16 times sine of 4x, because this is a constant with respect to the time variable. This is just, the Laplace transform of a convolution is the product of the Laplace transforms, so the inverse is also true. And now all I have to know is these three inverse Laplace transforms, and two of them are really, really easy. These are exponentials, and I claim that the inverse Laplace transform of something Gaussian like this is another Gaussian. I'm just going to write down the solution. So this equals u of x comma t equals, this inverse Laplace transform is e to the minus t convolution integral with this inverse Laplace transform, and this would be a whole 20-minute lecture to derive this inverse Laplace transform. I'm just going to write it down. This is kind of a textbook formula. It's not that interesting how to derive this one, but it is the inverse Laplace transform of something that looks like a Gaussian is another Gaussian. So it's e to the minus 1 over 4t 1 over 2 root pi t cubed, something weird like that, plus, and this is again e to the minus 16t sine 4x. And I am pretty sure somewhere there should be an x in here. Okay, so here is the part in the lecture where you might get a little frustrated because there is absolutely a typo somewhere in here, because I know that this was a function of x, and so somewhere here there should be an x. Maybe this should be like an x cubed, or there should be an x in here somewhere, okay? And so you're going to have to essentially go to your textbook or go to Wolfram Alpha or Mathematica or whatever and find the inverse Laplace transform of this function here. We're inverse Laplace transform with respect to s. And whatever you get, just substitute it in here and fix my typo. So it's actually kind of a nice little homework exercise because you'll see exactly what changes when you get the right expression for this inverse Laplace transform. I should have brought my textbook. But it doesn't really change any of the philosophy of how you solve this problem. You basically, Laplace transform in time to get this expression, which is an ODE in space with some forcing. My initial condition becomes a forcing term. I solve that ODE in space, and I get this expression that has a homogeneous and a particular solution. One half of the homogeneous solution is 0, so that my solution doesn't blow up as x goes to infinity. The other part of the homogeneous solution I solve with my boundary condition, and my particular solution I solve with my initial condition. And I just do that using kind of standard ODE techniques to solve for a bar of s using my boundary condition. A bar is just the Laplace transform of my boundary condition. My particular solution is just some transfer function times my forcing function sine, my initial condition sine of 4x. And when I go through all of that math, what I end up getting is my honest-to-goodness solution of my function u of x and t in the Laplace transform domain. So all I need to do is inverse Laplace transform this, and I get my solution in the time domain. Okay, and at least two of these inverse Laplace transforms are really, really easy because the Laplace transform of, the Laplace transform of e to the minus a t is just 1 over s plus a. So this Laplace transform and this Laplace transform are really easy. This one's a little bit gnarlier, but I'm just going to say, go to Wolfram Alpha, go to your textbook, type this in and get the inverse Laplace transform. That's the function that'll go here. It's going to look like a Gaussian in time. It's going to look like a time Gaussian. And so as time increases, the variance of this Gaussian is going to get wider and wider and wider, which is essentially going to smooth out my my solution as time goes on. So that's we've known this intuition for a while, that and I actually derived this in my Fourier transform solution to the heat equation. As time goes on, essentially the solution diffuses and diffuses and diffuses, and so you basically have this kind of Gaussian kernel where the variance increases or spreads as a function of time. But again, there's definitely a typo in here. I can see it clear as day because there should be an x somewhere. You can fix that by just typing this into Wolfram Alpha and plugging in that solution here. And then this will be the honest to goodness full solution in space and time of the temperature distribution on the semi-infinite domain. Okay, that was a lot, but I hope you found this to be kind of a little bit, empowering that you can actually do this yourself for these types. So try different initial conditions, try different boundary conditions. Make this cosine of 4x, or e to the minus x, and change your boundary condition, make this sine of t. Change things around and see how things change in this formulation. All right, thank you.